Hey guys, so today we're going to take a look at a game called Plinko. It's on the Price is Right game show, and so if you don't know Plinko, in the entire version of Plinko, you get to drop a chip into a board at slot A, B, C, D, E, F, G, H, or I, and then you get a chance to watch where that chip goes on the board. And down at the bottom, it can go into one of about, I think, 8 or 9, 10 spots. And each slot has a different dollar amount. And so what we're going to do is we're going to drop the chip from E, and we're going to look at the number of pathways that the chip can take to get there, to get to the gray square. So what you'll notice is I filled in a couple of the different particular places. So when you drop your chip from E, so here's the chip. Oops, come on, why is it not working? Chip from E, there we go. There's only one pathway for it to get into that first slot, and so that's why there's a 1 there. And so it's going to hit the black square below it and bounce one way or the other. It'll either bounce this way or it'll bounce this way, and there's one way to get to each of those gray squares. But here's where things get a little different. So at this point, that gray square or the chip can go either this direction, and so there's still just one pathway for it to get there, or it could go this direction, and there's actually 2 different pathways for it to get to that point. So it can go bounce down to this first one, then over to this, and here, that's one pathway. Or it can bounce here, go over to here, and then bounce this way and get to that same place in a second pathway. So there are 2 pathways to get to that middle square in that second row. So that's why we have a 2 there. So over here, this should be a 1 again. And then again, there's only one pathway to get to this square in the far right region. And so that is, it bounces, hits this first square, gray square, goes to this first one on the right, and then goes to here. That's one pathway that it can go. It's not going to go back up. It's not going to go side to side. It's going to move downward and diagonally from every square or gray square that you see. So what I want you to see is how many pathways that we can deliver here. So if we bounce down to here, then over to the left to the 1, over to the left to the 1, and then over here, there's only one pathway to get to that particular square. But if we drop down again here into that first and go back into the second, back into the third, it could go over here, and that's a pathway to get into that square box. And so the question is, how many different pathways are there to get into this square box? And so I'll give you a minute to think about that. Not a minute, a couple of seconds. And so hopefully you can see that there's more than one pathway to get to there. I've outlined one. A second pathway to get to that same box is to come down here, then to come down to this 2, and then to come into that particular area. So that's a second pathway. But there's a third pathway, and the third pathway is to come down into here, bounce to the right 1, then bounce to the 2, and then bounce here. And so there are a total of 3 pathways to get there. I hope everybody's understanding exactly what I'm doing at this point. And so the question is, well, what about this particular square? How many different pathways are there to get into that particular square as well? I will give you 10 seconds, 20 seconds to think about that, see how many pathways you can come up with. Hopefully you came up with 3 pathways again. And so the 3 pathways are, we come down here from E into that first gray box. we move over here to the left into that first, right into that gray box that's marked a 1. Then we go into the gray box that's marked a 2. Then into that particular box. That's one pathway we can use to get there. Another pathway we can use is we come down in here to the gray box, that first gray box, but this time it bounces over here to the right. It continues on out to the 1 and then bounces this direction to get to there. So that's a second pathway. And then a third pathway is it comes down in here into that first box, bounces here, but instead of following down the 1 pathway, it bounces to the 2 and then over into that box. That is a third pathway. What I'm hoping you see is that there's a nice symmetry going on with the number of pathways that you can have to get there. And if you look at the pathways, you can see that there's a nice symmetry there as well. And so because of that, there should only be one pathway to get to this rightmost gray box in that row. And hopefully you can see it fairly quickly. It bounces down into the first box, 1, 1 here, and that's the only way to get into that box. So I'm going to give you a minute to think about the next row and how many pathways it takes to get into that next row. Each of the gray boxes in that next row. How many pathways can I take to get there? I hope I'm going to erase all of my pathways and just put the numbers back in at this point. So I'm hoping that what you're seeing looks like this so far. And I'm hoping that you realize that there's only one pathway to the far left gray box and only one pathway to the far right gray box. I hope you ended up with 4 pathways into that second box in that row, and also the second to last gray box in that row. And then I hope that you realized or figured out that there were 6 pathways that lead you to that middle box. And so the question here is, okay, so how do I have to go through all the pathways again every single time to get to that place? And so the answer to that question is no. And so do you notice a pattern that you can use to get you these numbers or these pathways without actually going through and figuring out how many pathways there are? And hopefully what you realize is a couple of things. Number one, the very first and the very last are always 1s. And then what I'm hoping that you realized or started to notice is that if you take any 2 numbers in a row, so any 2 consecutive numbers in a row, and add them together, you get the number that's in the gray box in the row below that. So if you take these 2 numbers and add them together, that 1 and that 3, and add them together, you get this 4. The 3 and the 3 adds up to the 6. The 3 and the 1 adds up to 4. So we can use this sort of pattern to say, well, there should be 5 different ways of getting into that square. There should be 10 different ways of getting into that square. 10, 5, and 1. And then the next row should be fairly easy to fill in following this pattern. 1, 6, 15, 20, 15, 6, and 1. And then 1, 7, 21, 35, 35, 21, I also lost my mind there, 21, 7, and 1. And then 1 out here, this is an 8, 28. Let's see, that would be 56. Hopefully I'm doing my math right. 70, 56, 28, 8, and 1. And then there would be a 1 out here. I just didn't have enough room to put it. And then a 9. And this would be 36. And this would be 84. And this one would be 126. This one would be 126, 84, 36, 9, and 1. All right. And so these are part of the path. Those are the number of pathways that it would take you to get to that point. So the first question is, filling all the gray squares, you may notice a pattern. So that pattern is that we can figure out what the next row looks like by knowing the numbers in the previous row. And so what I did here is added the 1 and the 4 to get the 5, the 4 and the 6 to get the 10, the 6 and the 4 to get the 10, the 1 and the 5 to get the, or 1 and 4, excuse me, to get the 1. Here it's 1 and 6, 5 and 10, 10 and 10, 10 and 5, and 5 and 1. So hopefully you notice that pattern now. Hopefully you can see it more readily than having to try to figure out, oh my gosh, how many different pathways are there actually there. But I wanted to take you through at least the first three rows, 3 or 4 rows, to kind of get you acclimated to how these numbers come up, and then starting to see this pattern of, hey, if I take these two numbers in a row, add them up, I'm going to get the number in the gray box below and in between the two above. So it says, use the numbers you found to determine the probability that you launch your ship from E, you will land on the $10,000 mark. So how in the world do we figure that? So the $10,000 mark can only occur if I land here and if I land here. So there are 126 two times, ways of landing in those two marks. There's 126 paths to land in each one of those. And so the question is, how do we find a probability? Probability is determined by taking the number of favorable outcomes, and we divide that by the total number of outcomes. And so we know the number of favorable outcomes is that 120, I gotta make sure I have the right number here, yes, 126 and 126. The question is, what are the total number of outcomes? Well, the total number of outcomes would be the number of different ways we have to land in that row. And so if we add 1 plus 9 plus 36 plus 84 plus 126 plus 126 plus 84 plus 36 plus 9, what we should end up with is 512. And so our probability then for the total number of outcomes would be 512. And so this would be 252 out of 512, which is our probability then. So I'm sure some of you have seen this before, but I'm also sure that some of you have not. This set of numbers in this order is a lot of times referred to as Pascal's triangle. The reason it's called Pascal's triangle is because Pascal, he did not invent this. This has actually been known, this pattern of numbers that I've written in the gray boxes back on this panel has been known for probably close to 1,1200 years. They've known it in China starting back about 1,200 years ago. It's been found in the Middle East. It's been found in India. Pascal was the one who, though, linked this, as you're going to see later on, to counting techniques and to probability. And so because he was able to look at it in a different way, it's credited to him, but he didn't actually develop this. It's just credited to him for that reason. And so this next item, oops, dot there, sorry. This next item is just the first rows of Pascal's triangle. And so this very top row, you're going to see why a little bit later on, is what we call row 0. This next row with the 2 1s in it is what we call row 1. The next row with the 1, the 2, and the 1 is row 2. The next row after that is row 3, etc., etc., etc. So down here, this would be what we call row 10. So I have a series of questions. How is any entry obtained from the 2 entries immediately above it? That's what we did back here. So hopefully you've realized that if you take any 2 entries in a row and add them together, you're going to get the entry below and in between them. And so that's what this is referring to. Adding any 2 entries in any row will give you the next row and the value in between them. So what I want you to do is I want you to start adding up the numbers in each row. So in row 0, the sum of the numbers is 1. In row 1, 1 plus 1 adds up to 2. In row 2, 1 plus 2 plus 1 adds up to 4. In row 3, 1 plus 3 plus 3 plus 1 adds up to 8. In row 4, 1 plus 4 plus 6 plus 4 plus 1 adds up to 16. So the sum of the terms in this row up to row 4 look like, hopefully you recognize these as going, hey, wow, that's weird. This looks like powers of 2. And so we can think of 1 as 2 to the 0 power, 2 as 2 to the first power, 4 as 2 to the second power, 8 as 2 to the third power, 16 as 2 to the fourth power. And so when we get down here to row 10, these should add up to 2 to the 10th power. Interestingly enough, then, we can generalize this and say, well, the sum of the terms in any row in row n is 2 to the n. So the sum of the terms in row n is 2 to that row number power. And that's why we call this top row row 0, so we can generate this pattern pretty quickly and pretty easily. Next question. Now we want you to alternately add and subtract these numbers. So what does that mean? Well, the first row, there's only one number. So the first row, if we alternately add and subtract, we just get 1. But here what this means is start with 1 and then subtract 1. Well, that's 0. And then alternately add and subtract. So what does that mean? Start with 1, subtract 2, and add 1. And that's also 0. Alternately add. Start with 1, subtract 3, add 3, subtract 1. And yes, of course, that's 0. And so let's subtract 4, add 6, subtract 4, add 1. That also adds to 0. Let's see if that works down here in row 10. So let's take 1 minus 10 plus 45 minus 120 plus 210 minus 252 plus 210 minus 120 plus 45 minus 10 plus 1. And I'm going to give you a couple of minutes here, 15 seconds to get your calculators out and actually add and subtract those values. Does this, in fact, end up at 0? And so yes, it does. And so it looks like if we alternately add and subtract these numbers, the sum of those things is going to be 0, except for row 0, which has a sum of 1. Now we want you to add up the squares. What the heck does that mean? So let's take the top row, row 0, and we're going to square that term, and we end up with 1. So now we're going to take 1 squared plus 1 squared in row 1, and and that adds up to 2. And then we're going to take 1 squared plus 2 squared plus 1 squared and add that up. And that adds up to 6. And then we're going to take 1 squared plus 3 squared plus 3 squared plus 1 squared. And that adds up to 20. Now we're going to take a look at our Pascal's triangle. We're going to ask ourselves, do we see those numbers anywhere? And we go, oh yes. Here's a 1. Here's a 2. Here's a 6. Here's a 20. And so if I'm working in row 1 and doing this, or in row 0, excuse me, I get the row 0, that middle number. If I do this, if I square in row 1, I get the row 2 middle number. If I take a look at row 2 and add the sum of the squares, I get the row 4 middle number. If I take row 3 and add the sum of the squares, I get row 6 the middle number. There seems to be a pattern. So what if I took 1 squared plus 4 squared plus 6 squared plus 4 squared plus 1 squared? Question is that 70? And so the answer is yes, it is. So what we're getting is we're getting double the row, but we're getting that middle term in that row. What type of a geometric shape is formed if you connect the ends of the row to the total? So what kind of shape are you getting if you connect the ends of the row to the total? And that's basically just showing you the geometric sort of shape that's coming here is the symmetry, this sort of right triangle type of pattern. So the next one is pick a 1 in any row or column, doesn't matter, makes no difference. Pick a 1 in any row or column. So I'm going to start with this 1 right here. And then move diagonally downward. And I'm going to stop at the 70 simply because it's in black right now. And then add the numbers in that diagonal right here, including the 70. And so the question is, what's the sum of 1 and 5 and 15 and 55 and 70? And so, oh, that's a 35. Sorry, 35. 35, 35, and 70. And so what's the sum of those numbers? Well, we know that 15 and 35 is 50, and 70 is 120, so this adds to 126, and lo and behold, there's my 126. So I've heard this pattern specifically called one of 3 things. There's 2 of them that I agree with. There's one that I don't necessarily agree with. The one that I don't agree with is some people call this the candy cane pattern. I'm not sure it's a candy cane looking thing. Some people call it the stocking stuffer pattern, which I can kind of see that if you're thinking about hanging stockings at the Christmas time on your mantle. You can think of that. And some people refer to this as the hockey stick pattern, which I can kind of see as well. So the first one is the other 2 I can see, but that's the pattern that you should recognize in if you're taking 1 and coming down any diagonal. You can stop anywhere you want to. What the sum of those terms is going to be the next term to the right and then the next row down. So this is the first number of rows. One of the things that I do want you to see is really kind of cool, I think, is if you look at powers of 11, 11 to the 0 is 1, 11 to the first is 11, 11 to the second is 121. And so what I'm hoping that you're recognizing is row 0 is 1, row 1 is 11, or 1, 1, row 2 is 1, 2, 1. By the way, if you go to your calculator and do 11 to the third, it is exactly 1,331. And 11 to the fourth is 14,641. Where it seems to break down a little bit is when you get to 11 to the 5th. Oops, 11 to the 5th. But 11 to the 5th is 161,051. And so the question is, does it really break down at this point? But if you consider the numbers here as place values, if you read right to left, so as an example, 11 to the 5th, think of this as 1, 1. So 1, 1 would put that last digit as a 1. Think of this 5 as 5 tenths. Well, 5 tenths would make that a 50. So the second digit in from the right would be a 5. Think of this 10 as 10 hundredths. But the weird thing is 10 hundredths is 1,000, which means if I think of the next digit as thousands, I actually have one additional 1,000 over here, which means I have no hundreds left when I pull that 1,000 over to the next place value. That means I have 11 thousands, but if I have 11 thousands, I really have one more 10,000 with 1,000 left over. And this means I have 6 10,000s, which is 60,000, and I have 100,000. And so this actually does, if you think about this as being place values, it actually does work out really nicely if you carry over the next digit. So what does that mean about the next row? That means 11 to the 7th should be, the last digit should be a 1. The next digit in should be a 6. Oh, I think I went to the wrong row. No, 11 to the 7th. That's all right. We'll do 11 to the 7th. I just did 11 to the 6th here. We'll do 11 to the 7th. That's good. So 11 to the 7th, the last digit's a 1. The next digit is a 7. This means I have 21 hundredths, which means I have 2,100. So I'm going to keep the 1, and I'm going to make this next 35 a 37, because I'm carrying over 2 more thousands. So that means the next digit should be a 1. That means I have 37 thousandths. Well, I'm going to carry over 3 more 10 thousandths, which makes that a 38. And I'm going to keep the 7 thousandths. 38 10 thousandths means I have 380,000, which means I have 3 more 100 thousandths, and I have 8, whoops, don't want the apostrophe there, or the comma there, sorry. I have 8 10 thousandths to worry about. Now I have 2,400 thousandths, but I don't want 2,400 thousandths. That means I have 2,400,000. So I'm going to keep the 4, and I'm going to carry that 2 over and make that a 9. That means I have 9 millions, and the next digit I have is 1 10 million. And so that's why 10 to the 7th is 19,487,171. And you can check that on your calculator. So this really tries to work with, or it doesn't try, it, not 10 to the 7th, of course, it's 11 to the 7th. Thank you. So this really does accurately keep track of the powers of 11 if you think of each of the places here, each of the numbers that you see as a place value. So now you're going to get some time, and I'll give you time to do this later, but you're going to color in. And so what I want you to do is any number that's divisible by 2, you color in one color, and any number that's not, leave it as it is. And so what you should start to see is you should start to see a pattern here. So I'll let you do that a little bit later if you wish. And then the last thing is start at the top and add on a weaker diagonal. So what the heck does that mean? It means going down 1 row and 2 entries to the left each time. You should start to see what we call the Fibonacci sequence. So what the heck does that mean? So I'm sure most of you know the Fibonacci sequence, but what that means is start here, and that's the 1. Then we go to the next row, and we always start with the leftmost entry. And that 1, if I go down 1 and left 2, there's nothing there, so that's the second 1. Then I'm going to go to the the same row, but the first entry I haven't used, and I'm going to start here, and I'm going to go down 1, and I'm going to go left 1, 2. And I'm going to add those two numbers, and there's my 2. And then the next thing I haven't used yet is this 2, so I'm going to start there, and I'm going to go down 1, and I'm down 1 row, and I'm going to go over 2, and I'm going to add those two numbers, and there's my 3. I'm going to start over with another color, or I'm sorry, a red color, so the next thing I get to is this 1 that I haven't used yet in that second row. And I'm going to go down 1, and I'm going to go over 1, 2, so that 3, and I'm going to go down 1 and over 2, and oh, I got that 1, and 1 and 3 and 1 is 5. So I hope you can see what I'm doing here. The next thing I haven't used, the first one is that 3. So I'm going to go down 1 and over 2. So down 1 and over 1, 2 is that 4. Down 1 and over 2. And I'm going to add 3 and 4 and 1 is 8. So I hope you can see that Pascal's triangle actually has embedded in it what we call the Fibonacci sequence. And I hope you guys have talked about the Fibonacci sequence, but in case you haven't, we're going to go to the next one. So the next one would be, start with this one, go down 1 and over 1, 2, go down 1 and over 1, 2, go down 1 and over 1, 2. Oh, I can't go anymore because I'm on a 1. And so 1 and 6 and 5 and 1 adds up to 13. And we'll do one more. So now the one I haven't used is I'm going to start with this 4. And I'm going to go down 1 and over 1, 2 is that 10. Down 1 and over 2 is that 6. Down 1 and over 2 is that 1. 4 and 10 and 6 and 1 is 21. If you've not seen the Fibonacci numbers before, basically the way we generate the Fibonacci numbers is we start with the two 1s, and then we add those two 1s to get the 2. And then we take the 1 and the 2, and we add the 1 and the 2 to get the 3. So we take the two previous terms, starting with the two 1s, and we take the two previous terms and add them together to get the next term in the sequence. But I wanted you to see that the Fibonacci numbers are actually embedded within this particular triangle. So, your homework is to start with Betsy the bug. And again, what you're going to do is you're going to try to figure out the number of pathways it takes. Betsy's going to start here at point O and going to continue to travel down. So how many pathways can she go to get to A? And I'll just give you a clue. There's only one pathway to get from O to A. Okay? So there's only one pathway to get from O to A. So I want you to do the other 4 here. Then on this page, you're going to buy some pizza from a new pizza place. And they offer anchovies, broccoli, cabbage, and duck meat. So the question is, if you order a 1-topping pizza, you're only allowed 1, how many different types of pizzas can you get? And I'll go through this first example with you. So you can either get a topping, you can either get a pizza with anchovies. That's one pizza you can get. Or you can get one with broccoli. The third type you can get is one with cabbage, and the fourth type you can get is one with duck meat. And so there are 4 different types of pizzas that you can order here. Then the next one is, well, how many different 2-topping pizzas can we get? Well, we can order one with anchovies and broccoli as an example. So that's one option. So the question is, how many different types of pizzas can you order here? And then lastly, I want you to use your calculator. So if you go to menu, and then go to number 5, which is probability, and then 3, which is combinations. I think you guys talked about combinations last year. So we're going to do the NCR command, and then we're going to do 4, 1. And you're going to put the number in here that you get when you type these things in. And then what you're going to do is you're going to compare your answers for number 1 with Betsy the bug, number 2, at least these 3 with 1-topping, 2-topping, and 4-topping pizzas, along with the number of combinations of 4 objects 1 at a time, 4 objects 2 at a time, and 4 objects 4 at a time. And then you're going to take a look specifically, you're going to write down the first 6 rows of Pascal's triangle and see if you can see the number of pathways that Betsy the Bug made, the number of toppings of pizza, the number of pizzas you can order with those number of toppings, and the number of combinations in there. You're going to see if you can see those in Pascal's triangle. And so that's why the last question is, how do these previous examples relate to Pascal's triangle? And that's where you're going to start then on Friday. So your homework is to finish Betsy the Bug, pizzas, and use your calculator to figure out the number of combinations of 4 objects 1 at a time, 4 objects 2 at a time, 4 objects 4 at a time. And then specifically, how do these examples relate to Pascal's triangle? Okay? So that's your homework. It should be relatively quick, fairly painless. And so I will see you again. Have a good rest of your day.